Record. You're recording. Okay, we're good to go. One of the questions from the homework that someone brought up in the last class that I wanted to just kind of take a look at real quick. Really hard to see. Hard to see, right? Is that better? Yeah, everybody's good. Okay. This is from the 1.2 homework. This is kind of our, maybe first chance to see a function kind of in action, like what we would do with it in the real world, right? An application. We've got this bicycle manufacturer. They have a fixed cost of $100,000, and then it costs them $200 to produce each bicycle that they make, right? So the fixed cost, that's maybe startup, buying a building, developing the thing in the first place, whatever. That happens no matter what, no matter how much business they do. And then on top of that, material, labors, whatever, it costs $200 to actually build each thing they build. We're simplifying some stuff a little bit, of course, but this gives you kind of a good idea of how this stuff really works. The total cost for the company is then the sum, so adding, of the fixed and variable costs. What we want to do is write a cost function as a function of the number of bicycles produced X. So we're going to use the variable X, and what we're going to use it for is to represent the number of actual things that they're making. There we go. And what that's going to give me is the total cost, right? Their total expenses, in other words. Cost is always going to be kind of from the perspective of like you, right? I'm putting myself in the shoes of this manufacturer. It's my expenses when we talk about cost. So how would we do that? What would this function look like? It's a sum, so we're definitely adding.
Fixed cost was 200 times X.
So the fixed cost, 100,000, plus, because it's the sum, and then the variable cost, you said 200 times X. It costs $200 to make each one. So if they make 3 of them, that's 200 and 200 and 200. Or a better way to write adding it a bunch of times is to just multiply instead. Right? So, implied multiplication there again. This is, similar, or that part of it, the 200 times X is similar to the paycheck thing we talked about the other day, right? Same idea and same reason. So that would give you the total cost, right? It's your initial startup overhead stuff plus, well, how much you actually spent on making the thing. Okay, now that should look kind of familiar. That's a linear function. You've seen those before. This is the y-intercept. The slope is 200, so you go up 200 for every one you go over, right? That kind of thing gives you a nice straight, very steep line. Okay, then find C of 90 and interpret what it means. So how do we find C of 90? Put 90 where X is. That's it. 100,000 plus 200 times 90. And then again, that once I've made that substitution, once I've plugged it into the function, it turns it from this kind of abstract idea into just an arithmetic problem, right? 200 times 90 is 18,000. I think, yeah, 3 zeros. 18,000 plus 100, so 118,000. Okay, that's the finding it part, right? We found C of 90, there it is. C of 90 is this number. Now we need to interpret. The interpreting part, that's a little bit higher level, but that's also the thing that we probably are going to be like leaning on the most when you leave this room, right? The real world and your job and your, studies in your discipline, whatever. The thing that you need to be able to do is like interpret numbers and explain what something's telling you, right? So what is this telling us? What do these two numbers mean? Go ahead.
When you use 90 for your cost per type, you have to add in 100,000 plus the $200 it costs to make per byte.
Okay. So let's think about units here, maybe. What is 90?
When you make 90 bikes.
90 is the number of bikes, right? What's 118,000? The total cost. It's the money, right? So this point, this ordered pair, this XY pair that go together, right? 90, comma, 118K. What that tells me is that in this situation, it costs them $118,000, which I can't write here probably, to produce 90 bicycles. Right? What that says is that when they make 90 bikes, it's going to cost them $118,000 to do that. Right? So hopefully, if we looked at their like revenue and profit and stuff, ideally they would want those numbers to be big enough to account for that cost. Right? We'll get more into that idea later, but for the moment, just the interpreting part, and really anytime you see interpret in directions, it's just going to mean, okay, you got this point, right? This XY pair. What I want you to do is turn that into a sentence that explains what's going on, right? Here, I would say something like, when they build 90 bicycles, it costs them $118,000 to do that. Or it costs $118,000 for them to build 90 bicycles or something, right? Connecting words that show that you know what the units are and kind of what the situation, what the function's describing, right? Probably every test I give you, every, I mean, not every like quiz, not everything, but every homework assignment, just about, there might be a couple exceptions. Every test, every like major thing that we do, somewhere you're going to see something that asks you to do this. And when I ask you this kind of thing, I mean, there's kind of two parts. There's one, the mechanical part, finding this, right? But the interpreting is the bigger part of it, right? So if this question was worth 10 points, this is going to be like 3 of them or something. This is going to be like 7 of them because, kind of the bulk is understanding what that actually communicates, right? Okay, is that all clear? Do you have any questions? Okay, like I said, it's going to show up on homework and stuff kind of throughout. So it's something that we'll get plenty of practice with. I'll make sure we're spending a good amount of time on it in class. I'm not going to keep writing with this tiny eraser. All right, we left off whenever the last time we were here was, Tuesday. Right about here. And the idea of describing domain and range, right? So domain, again, the word is referring to the set of all the input values for a function, or all the x values for a function, all the independent values of the independent variable that it can take. So domain's describing that. But often when we talk about domain, we're going to need to be able to sort of compactly write down or describe a range of, sorry, I shouldn't use the word range again, a sort of continuous like group of things, right? A bunch of stuff all together, not just something I can list out, right? Last time we did or I guess Monday maybe, we did the thing where we talked about, pairing up every person with their height, right? Well, if you do that, you're just talking about 25 people or whatever, so you just write the names down, right? You just list them. When we're talking about the domain of a function, we're probably talking about a bunch of stuff, and not just the like obvious things, but also stuff in between, right? So think about like this number line that I've got here. I know that it might be hard to tell what's shaded on the black and white copy, but shaded from here to there. This doesn't just mean -1, 0, 1, and 2, and 3. It means all the stuff between them as well, right? The marks on there just kind of so we can keep track of where we are, right? It's like a signpost. But we mean everything between as well. So it's 0.374, like that's in there too, right? So if we want to think about how we could describe that, right? First, you know how a number line works. You read it from left to right, like you read other stuff, right? So if you're trying to describe this picture to somebody who can't see it, right? You're trying to tell your mom on the phone what this number line looks like. I don't know why, but like you are, right? We're trying to just describe it in English. How can we describe in English what's on that number line?
All numbers between -1 and 3.
Perfect. Everything between -1 and 3, right? The reason we shade it in is we mean all of it, right? Somebody last hour said like -1 through 3, something like that. That works too, right? If I know how the number line works, that I'm going to read it left to right, I could do that same thing by, really what I need to know is where does it stop and where does it start? Sorry, I did those backwards. Where does it start and where does it stop? Okay, well, where it starts is -1, where it stops is 3, and what I want is everything in between, right? Okay, now there's one other like subtle difference about what happens here and what happens here. What is it? One of them's okay, one of them's equal to, the other one's not, right? This filled in point at -1, that means that's included, that's equal to, that's okay, -1's there. 3, well, 3, that open point, that hollow circle, that means you can get right up next to it, but you don't actually get there, right? So 2.9999999, whatever, that's included there, but 3 itself is not. That makes sense? Kind of like if I walk halfway to the door and then walk halfway to the door again and keep doing that, like in some sense, I never get there, right? I stay with my nose a molecule away from it or whatever. That same idea. That's weird. I get that, but it's right up next to it, but not the thing itself. So 2 ways we can write that, 2 notations for writing this down. One is called set builder. Set builder just means that we're going to write a set, so curly braces, right? Because curly braces always mean this stuff goes together. It's a set. I know that this kind of looks intimidating, right? The set builder thing, because it's got all kinds of symbols and stuff, but it's a set. It's a set of stuff called X. So we're just naming it, right? If I was talking about Y, I'd call it Y instead there. This vertical line, you can read like such that, or you can read it like where, or something like that. It just means I'm going to give you some rules for what I want X to be, right? It's the set of things called X where there's some restrictions coming, right? I'm going to describe what it means, what X can be. So the set of all X such that, and then we describe with inequalities. Everybody remember how inequalities work? If I've got 1 fish over here and 3 fish over here, which way does the thingy face? That way, because it's a hungry shark. And it wants to eat the side with the more fish, right? Okay, good. So what does this say then? That says -1 is smaller than X or equal to, that's the line underneath, right? So -1 is smaller than X, or X is bigger than -1. What does that say? X is smaller than 3, right? 3 is bigger than X. So X is bigger than -1, smaller than 3. This one can be equal to, that one's not. So again, we could read this as like between, right? It's between -1 and 3. With, again, one included, the other not. What? It's, again, it's not an absolute value. It's the such that, or so that, or, with the condition that, so it's the set of all X where X has got to be between -1 and 3. Sometimes you'll see that written with a colon instead of a vertical line like that, but it means the same thing, right? It's just saying, it's a like clarifying, adding more information kind of thing. We're not going to use set builder nearly as often as we will use interval notation. You'll see it come up in a couple of places. I know, again, that it looks kind of scary, but don't get intimidated by it. It's just using inequalities to describe what's happening. Interval notation, that's going to be kind of our main like bread and butter. That's our jam. We're going to use interval notation a lot because it's kind of as short, brief, compact as you can possibly be in describing the thing. What interval notation tells you is where do you start and where do you stop. That's it. You separate them with a comma. So where do we start here? -1. Where do we stop? 3. We're going to read it left to right, just like you read the number line, just like you read anything else. So I would write that like this. Start at -1, stop at 3. So we separated with a comma, that's it. The other thing is that we got to clarify what happens at the ends, right? One's equal to, the other's not. We do that with a square bracket or parentheses. So square bracket means included. You can also read that as closed. Parentheses means not included or excluded or open, right? That you get right up next to it, but don't actually reach that point. The brackets versus parentheses thing, that's very much a, like, you just got to get used to it thing, right? So, you miss a couple on the homework, you figure it out, like, it's fine. There's not really a reason for one to be one way and the other to be the other way. It's just, how we do it, right? It's just the convention. Okay, so how would I write then in interval notation? What's on this number line? Again, I'm just putting those there for like reference, right? What's that? Yep, with a bracket. Yep, perfect. Okay, now what if I added that? And I want to use interval notation to describe everything that's shaded right there.
Put a comma between the bracket, then start a parentheses.
Okay.
Go from 1
Shoot.
to infinity and parentheses.
1 to infinity, because it continues on, right? Parentheses for infinity always, because you can't like get there and stop in the same way, right? Infinity is kind of its own thing. It's not really a number. So we just think of that as sort of continuing on. I can't reach it. Now, those two things are separate, right? There's a gap between them. They're disconnected. The way we take disconnected or disjoint is the math word for that, sets like that, and sort of glue them together and say, like, I want this and this, is we use a union symbol that looks like that. When you're entering stuff in my math lab or whatever in the homework, there's a little union symbol down in the little like math symbol tray thing. There's also an infinity there. It's not just a letter U, it's kind of its own little like thing. I say that because the homework's going to kind of wrong if you like type a letter U, but
we didn't have any of those kind of problems on it yet. So
yeah, well, it's coming at some. Sorry, sorry, I almost died. I don't know what happened there. It's coming at some point. So yeah, when you need it, when it shows up, it'll be there. But yeah, that's how you would do that. That's how you kind of glue things together that have like a gap between them. Okay. Okay, cool. All right, now this last example 4, right? This is kind of putting everything together. So we want to look at the graph that's on that QR code on the front. This one. And we want to figure out the domain and range for this thing. And then do some other stuff. So if I take a graph like this, where we're in 2 dimensions all of a sudden, right? It's not just a single number line, it's a number line this way and another number line this way, and I got to sort of keep it all straight. First, the horizontal one is which axis? The X, yeah, the way we set it up is we put the X on the horizontal and the Y on the vertical. So when we talk domain, we're talking X, which means I'm looking at the horizontal axis. So if I want to figure out the domain here, what I'm trying to figure out is what X values does that thing cover or include or use or go through? Where does it exist, right? Where is the function defined? I'll probably, start saying often like, where does the function live? I mean, like, what does the function know how to accept, right? What does it know how to take as input? How can we figure that out?
Separate each parenthesis between the X and Y.
Like the points?
Yeah.
Okay, so if we had a list of all the points and we just peeled all the X values off, then that would give you the domain. What's maybe problematic about doing that here? About like if I was actually going to do that. Can I actually list all these points?
no, because there's an infinite amount between 0 and 1.
Because it's a continuous connected thing, there's an infinite number of them, right? It's not just like, 0 and 1 and 2. It's everything in between them as well, which is why I draw it as a solid piece. So it's 1.1 and 1.111 and 1. It's all of those, right? We can still use that idea though to sort of imagine what's going on. I just can't actually write them down. Well,
Did you just graph the points that actually touch?
Graph the points it actually touches. Okay. Again, there's going to be an infinite number though, so it's going to give us like a shaded, thing like we had before on the number line. one way to look at that is if I imagine this thing's made out of like Play-Doh or like, some like soft material like that. If I crush it down onto the x-axis, right? So take the whole thing and just smash it down this way. The stuff that gets covered up, that's going to be the domain, right? Oh, the projector's kind of ghosting a little bit. You can still kind of see the graph on there a little bit. That's useful actually. But I kind of imagine smashing this thing down. Or if you want to think about it as like, where does its shadow fall? Maybe on the x-axis, something like that. What does it actually go through? Well, where do we start? -1. Where do we stop? 2. Everything in between is in there, right? There aren't any like gaps or anything like that last one. -1, there's an open point, an open circle. And 2, there's a filled in solid one, right? So what's the domain then? Start at -1, stop at 2. And how do we deal with the endpoints?
Parentheses on the left, and bracket on the right.
Yeah. -1 to 2, open or parentheses for 1 or for -1, and then closed or a bracket at 2. That is what Kayla described, like, writing down all of the points and peeling the x coordinates off. It's just that, again, there's too many of them for me to actually like physically write them down, right? Because they're all connected. But that's what this notation is for. Like, that's exactly why we have this. So we can describe everything between here and here, not just the like nice, pretty points that we would, mark if we were putting tick marks on our paper or whatever. Okay. What about the range then? How do we do that same thing for the y values? You basically do the same thing, right? Now imagine it kind of smashing in this way and look for the y values that get covered up. So where's the lowest point on the graph? -1. And where's that's lowest. And where is the highest point? 3. -1, all the way up to 3, and then it stops, right? Okay, so start at -1. Stop at 3. Does anything weird happen in the middle? Are there any points left out, excluded, that we hop over? What, this guy? Does that matter? Do I care? Do I need to do some kind of union thing and jump over that? Why not? Because it gets covered up somewhere else, right? We're talking about sets. Sets are always a like, are you in or out, yes or no type of thing, right? It's not how many times it shows up, it's does it show up at all. So this point right here, yes, this one misses it, right? John, I don't know why I'm pointing with the stick at a thing that's a foot away. Here, we don't include that, we jump over it, but it gets picked up somewhere else, right? So the thing still goes through 0, it just does it over here, not over here, but I don't really care about that. As long as 0 is in that set somewhere, as long as there's a point with whose y value is 0, which there is right here, then it should be in the range. So it's everything from -1 to 3. And how should I do the endpoints? Does it look like it actually goes through -1?
Yes.
Yes. This will change a little bit later in the semester. We'll have to like come back to this, concept and kind of, work on it a little bit more. But for now, if a thing looks like it goes through somewhere, then it does. If it's not meant to, it will really, really look like it's not meant to, right? Like there will be something, sort of calling your attention to that. This looks like it goes through -1. I don't see an open point or whatever. So it goes through -1. So bracket then. And what about 3? There too. And there I've actually got like a point, underlining that. Yeah.
So why do you go down to -1 and not just to 0?
Because we're talking about the y values, right? So for range, I only care about the y values. The x value is like telling me when that happens, right? When it gets to -1. But for the range, the thing that I'll the thing I want for the range though is the actual y value itself. So it's like the lowest, the lowest point that the thing ever gets, y value. And wouldn't that, like the range would look the same if this thing lived over here, right? Because it's just talking about the y values. And in the same way, domain only talks about the x values. So if you took this thing and, you know, this exact picture and moved it down here or something, that's not going to change the range at all if I just move it straight down. Okay. All right. The other things here are all going to come down to either I'm giving you an x value and I want you to find the y, or I'm giving you a y and I want you to find the x. What is 1 there in part C? Is that an x or a y? It's an x. So your answer then is going to be the y that goes with it. So look at the graph, find x equals 1, figure out what the y is. So I look at the graph, I go to x equals 1. What's the y value that goes with it? 0. So it's just, you know, describing the coordinates at that point. I gave you one of them, I want you to find the other. So f of 1 equals 0. When does f of x equal 3? Now what am I giving you? That's a y. So now I go, I find y equals, no, I didn't need to stay. I find y equals 3, and I figure out where the graph is, and the x value would be 2. So when is f of x equal to 3? When x is 2. X and y intercepts, same idea. X intercepts are going to be where you hit the x-axis. Sorry. Y-intercept is going to be where you hit the y. Dang it. Y-intercept is going to be where you hit the y-axis. So what's the x-intercept? One for sure, right?
Can it be 2?
There can be 2. There can be as many as you want. What's different about this point, though? Doesn't actually quite get there, right? In some sense, if I like zoomed in far enough, I could see a little bit of gap there, right? Where it doesn't quite get high enough. It doesn't quite get to that point. So if that point was filled in, then it would be -1 and also 1. Since it's open, though, it's just going to be that point over there, right? So the only x-intercept is there at 1. What about the y-intercept? -1. Yep. X and Y intercepts, one nice thing, and one thing that you know, we'll probably need to lean on from time to time is that they've always got 0 as their other coordinate. So 1, 0, 0, -1. That means if instead of a graph, you have an equation that's describing a function, or like a, you know, formula, that version of a function. If I want to find the x-intercept, I can let y be 0 and then, you know, do some algebra stuff and figure out what x would have to be. If I want to find a y-intercept, I can let x be 0 and do some stuff and figure out what y is. Right, so that's how you do that, you know, symbolically if you have a function kind of written out as a formula. Okay, does that all kind of make sense? Domain, range, finding an x given a y, or finding a y given an x. That's basically what all that comes down to. All right. This, like what we just did, you know, coming up with the graph. I know I gave you that one, but you know, we'll do some stuff also where we need to come up with the graph for ourselves later on. But getting the graph, interpreting the graph, finding an x given a y, finding a y given an x, talking about intercepts. This and kind of the things that like connect to it, right? Idea wise, that's probably half-ish of what we're going to need to be able to do this semester in terms of, you know, earning points and doing things. This and the things that kind of come out of it is about half of it. So yes, we've spent, you know, most of 3 days on this one section, but it's because it's important, right? So if any of this is still giving you trouble once you go in to do some homework and like work through the stuff in 1.2, please let me know. We'll talk about some things some more and see if we can iron things out. Some of it, you know, you'll kind of develop and get over time as well. Okay, sound good? Do you have any questions for right now? Okay, great. The next week or so, we're going to talk a lot more about graphing. So graphic, we're gonna look at first just two examples, and we're gonna do a whole bunch of stuff with them to kind of figure out the idea here and what's going on and kind of the main like concept, the big idea. So that QR code, if you scan that with phone or tablet or whatever, that'll pull up a graph that has these two functions on it. It will look something like this. You can toggle the two off if it comes up with both of them on. You can toggle one of them off. Just click on it. This is the graph of f of x or y equals x squared. Sometimes we'll call that the squaring function. It's the function that takes a thing and multiplies it by itself, right? Or squares it. Takes two copies of them and multiplies them together. That's its graph. I've marked a couple of points on it just so that we kind of have them as reference. There's nothing particularly, interesting or unique about these values themselves, but I did pick, the ones I did for kind of a reason that you'll get to look at in a minute here. But let's take the next 5, 7, something like that, 5-ish minutes. You guys in, groups of 3 or 4 get together, talk to each other. Think about this function, finding its domain and range. That should be, something achievable now. The part C, the coordinates of some key points, just the stuff that's marked here, like don't feel like you need to copy those down or anything. Just, look at those. But then part D is where things kind of, go up a little bit in terms of what it's asking your brain to do. Do you notice anything about them, right? So we're looking for patterns and things in the points that I decided to give you. So let's take a couple of minutes and do that. And then part E there, find f of negative x. You should do that as well. The last part there is a vocab word, so I'll have to give that to you. But take a few minutes, think through that, talk about it with each other and those around you, and we'll see what we come up with.
Okay, I don't need to hold that up right now. So.
Negative. Oh. Yeah. That
I don't use it. Always. It does have always keep going.
this was. It's all the domain.
Yeah, you don't really need to write. Yeah, it's just, there's nothing special about those points. It's just that I'm putting them there so you can hopefully notice the pattern.
What do you think negative 1 is? Yeah, because that's.
Thomas,
Yeah.
you're talking about, for F, you're talking about inverse function. Right?
No.
Are you talking about, just the name of it for my one?
It may not be a, term you've heard before. It's just the word that we're gonna use to describe it. So, yeah. That part you probably don't know how to do.
We'll just go.
Okay, let's talk about the domain and range. Domain and range from a graph, this is a thing that, if not right this moment, then in the next, several days, should be a thing that's like just a procedure that we know how to do. Like a thing we could just, look at and find without it being like a big, barrier. Like some of these are think about it, figure stuff out type questions. These, again, if not now, then soon, should be just kind of a procedure that we can just do, right? So the domain, we always mean all the X values, right? All the stuff along the horizontal. If you want to think about that as, okay, if I took this graph and pushed it all down onto the X axis, or, where does the shadow fall or something like that, you can do that. But it's which X values does it go through? So what do we think? Okay, -3 to 3, those are the places where I actually marked stuff out. But what happens beyond that?
It keeps going forever.
It keeps going, right? If I was going to draw this by hand, I'd stick a little arrow ends on that maybe to show that it keeps doing what it's doing, right? Anytime we graph a thing with a computer, a calculator, whatever, it's only going to show you part of the picture, right? By default, it usually goes like 10 in every direction, and that's what you see. But if it's just going like clean off the edges of the graph, generally it's safe to assume for us in this class at least, that it's just going to keep doing what it does, right? There'll be some times where we got to move stuff around, adjust and whatever. But usually if we just look at a graph like this, especially if it's one I've made and I'm giving you, we're going to assume it just keeps doing what it's doing after the screen cuts off, right? So if those continue on, what does that change about the domain? One of them, it goes that way for as long as you want, right? So, I'm the y-axis here in the middle. Continues to the left as far as you want. What that means is if I'm talking about starting and stopping, it doesn't really start anywhere, it just kind of always is, right? So how can we write that? Negative infinity. And for infinity, we always use parentheses again because you can't get there and stop, right? It just keeps going. And then the same idea that way, it continues on to the right. You guys may not appreciate this, but I think so far I'm doing a very good job with my left and right because I am facing the opposite direction than all of you. So I have to remember to call this my right hand and this my left hand. It's harder than you think it is. Most of the time I goof it up when I'm not in the classroom standing in front of a bunch of people who are facing the other way. Right? Yeah, anyway, it's a struggle. Okay, that would be the domain. That also means everything, right? All real numbers. The fancy math symbol for that is a capital R that's like double struck on the vertical part. That means all real numbers also. You might see it once or twice in the homework or something. I'm just going to say all real numbers or write this to describe that. What about the range? Same idea for the Y's, right?
But it has
There is a lowest point. The lowest point is 0. Is there a highest point? No, we keep going. There's an arrow pointing up. What should happen at 0? Because we actually go through it. I know that we actually go through it, right? I'm not even just assuming this time. There's a point marked at 0, 0. So like, I know that it goes through there. Okay, again, the key points thing, I just, I'm calling attention to a few of these. Now, part D, this is where things get a little more complicated. Do you notice anything? Right? What do we see? What do you notice about these points? Okay.
It's symmetrical.
Okay. Reflections, symmetric. Can somebody expand on that a little bit? Like, what do you mean when you say it's a reflection? What do you mean when you say it's symmetric?
reflects across the y-axis.
Okay. Reflects across the y-axis. Y-axis is right here. So reflecting across that, you mean
Yeah.
doing something like that? Okay. If I just look at 2 of these, right? 1 point and its buddy. What's different and what do they have in common?
The X values are opposite.
The X values are opposites. right? 2 and -2. Negatives and positives, you can think about as opposites in a like number line direction kind of sense. The value is the same, 2 and -2, right? They're the same size, absolute value if you want to describe the distance, that's the same. That means they're the same distance out. So one's right here and one's right here. The arms are pretty much the same length. They're just in opposite directions. Okay, that's what's different. What's the same? The distance part. They're squares of each other. When you square 2, you get 4. When you square -2, you get also 4 because negatives cancel in pairs. So they're the same distance out, but in opposite directions, but they end up at the same height, right? So the y values are the same, but the x values are opposite. That's symmetry. That's reflecting across the y-axis. Okay, is that just true for that pair of points I looked at? No, it's also true for all the other pairs I marked. That's why I marked these, these 3 sets of pairs, so that you can notice that if I go out this far this way and I go out that far the other direction, they end up at the same place, right? They end up at the same height. That's true for everything. It's even true for the points that are not very pretty that we don't want to think about, like 1.37962, whatever, right? It's bunny over here, it's at the same height. That's the thing that we want to notice. So there's symmetry about or with respect to the y-axis. The y-axis acts like a mirror. It acts like the middle of this graph, right? The reflection thing, if you want to think about it that way, if I held the y-axis still and flipped this picture over, would it look any different? No, it'd be exactly the same. If I drew this graph on a sheet of paper and folded down along the y-axis and like held it up to the light or something, what would you see? You'd see just one of those, right? They'd line up perfectly. That's what's going on there. That's y-axis symmetry. That's reflecting about the y-axis and getting the same thing. Okay, let's see what this looks like symbolically. If I find f of -x, what that means is where there was an x before, replace it with -x, right? Just plug that in, make that substitution. What the function does is square the thing. So f of -x is -x all squared, but that means take 2 of them and multiply them together. And what happens when you do that? The negatives go away, right? The negatives cancel, and what you're left with is x times x, which is also known as x squared. Okay, cool. That's the just like mechanical symbol pushing part, right? That's just me doing some algebra. I replaced x with this thing. When I did that, I could clean it up a little bit. I got x squared. The important part here is that we've seen before somewhere else, right? That was also the way the function was defined in the first place. They're equal. Being equal means they are when I make a big deal about the word equals, I'm almost always going to be looking for someone to say, same, they're the same, right? They're identical. I can't tell them apart. What that says is that for any x value, not just those couple that I marked, right, and made kind of look like they're a big deal on the graph, they're not really a big deal. They're just convenient and help us see the pattern. But what this says is that anything, anywhere, right? If I go out 1,000,000 that way and 1,000,000 that way, I'm going to get the same y value back, the same height, right? It's going to work the same for all of them. That's y-axis symmetry. That's reflecting about the y-axis and getting the same thing. Functions that do this are called even. Even functions all have y-axis symmetry, and any function that has y-axis symmetry is an even function, and f of x and f of -x are identical. Those 3 things all kind of mean the same thing, right? They're all kind of from different perspectives, but they're kind of communicating the same information. Okay, so those are even functions. All right, I know we're just about out of time, but let's look at the other one real quick, and then I'll leave that for you to finish up. But x cubed. Well, what's different about x cubed?
Not, symmetric.
It's not symmetric the same way, right? What happens with the square is that two negatives cancel and give you back a positive, right? Well, now we're talking about cubing, so 3 copies. So if you start with a positive, you're gonna get positive back. If you start with a negative, you're gonna get a negative back, right? So what's different here is that the symmetry works differently. Every point's still got a buddy, and those are the ones I marked, but now their relationship is a little bit different, right? And how they work. And what I would ask you to do, so I'm gonna ask you to like finish or attempt number 2 there, that second example, doing all the same stuff with X cubed. Take your best guess at the last part, what it's called. You can probably, figure out what you get there, but look for how they're related to each other. Look for and think about like how the symmetry works, how we might describe that, and definitely do the like domain and range there. Okay. Okay. So homework is, finish number 2 on the notes, and also the 1.2 homework in my math lab. Again, you should be able to knock all that out, right? If there's something you have questions about or whatever, email me, but get in there and do that as soon as you can. All right. Y'all have a good day. I will see you on the next day that happens